Settle in, close your eyes, and let us journey together to the very beginning of everything. The universe, as we know it, is a place of almost incomprehensible vastness and awe-inspiring beauty, a cosmic ocean stretching billions of light years across and containing countless billions of galaxies, stars, and planets. It is a place of profound mystery and wonder. But have you ever wondered, in the quiet of the night, how did it all begin? The most widely accepted scientific explanation for the origin of our universe is the Big Bang theory, a truly groundbreaking and elegant idea that provides us with deep insight into the very beginnings of space, of time, and of everything that exists within them. The story of our universe's origin takes us on an incredible journey back in time, approximately 13.8 billion years, to a moment of unimaginable density and unfathomable heat. Before the Big Bang, the universe as we know it, with its stars and galaxies, simply did not exist. In fact, even the term before is somewhat misleading, because according to this theory, the very concepts of time and space only came into existence with the Big Bang itself. According to the theory, our entire universe began as a singularity, a single point of infinite density and infinite temperature, where all matter and all energy were compressed into an incredibly, infinitesimally small space. Then, this singularity suddenly began to expand in an event that we have come to know as the Big Bang, an event that created the very fabric of space and time itself as it grew. Now, the term Big Bang might make you picture a violent explosion in the dark, but it is important to understand that it wasn't an explosion in space. It was the expansion of space itself. Imagine a tiny folded piece of cosmic fabric that suddenly began to unfold, stretching rapidly in all directions, causing everything contained within it to move away from everything else as the universe expanded. In the very first fractions of a second after this great unfolding, the universe was an unimaginably hot and dense place, a seething, chaotic soup of pure energy and fundamental particles. During this primordial period, known to physicists as the Planck era, the fundamental forces of nature that govern our universe today, gravity, electromagnetism, and the nuclear forces, were all believed to have been unified into a single, perfect force. As the universe continued its rapid expansion and began to cool, these forces started to separate from one another, and the first fundamental particles, like quarks and electrons, started to form. About 1 second after the Big Bang, as the cosmos continued to cool, these quarks combined to form the first protons and neutrons, the essential building blocks of all atomic matter. As the universe expanded and cooled even further, these protons and neutrons fused together during a process known as nucleosynthesis, which formed the nuclei of the very first light elements, primarily hydrogen and helium. However, it would still take hundreds of thousands of years before these newly formed nuclei could capture electrons to form the first stable, neutral atoms. This early period of the universe's history is often referred to as the Cosmic Dark Ages, a time when no stars or galaxies had yet formed to illuminate the cosmos. The universe was filled with a diffuse glowing cloud of gas, and light itself was effectively trapped, unable to travel freely because it was constantly scattering off all the charged particles. But this all changed about 380,000 years after the Big Bang. At this point, the universe had finally cooled enough for electrons to combine with the atomic nuclei, forming the first neutral atoms in a process known as recombination. This was a truly pivotal moment. For the very first time, light was set free from its long captivity. This ancient light, released at the dawn of the universe, is something we can still detect today. It is what we now call the cosmic microwave background radiation, or CMB. It is a faint, gentle, almost uniform glow of microwave energy that permeates the entire universe, a beautiful and ghostly afterglow of creation itself, providing us with a remarkable snapshot of our cosmos in its infancy. The discovery of this cosmic microwave background radiation, first detected by Arno Penzias and Robert Wilson in 1964, stands as one of the strongest pieces of evidence supporting the Big Bang theory. Its properties, this faint and nearly uniform glow, perfectly match the predictions made by the theory. Another key piece of evidence comes from the expansion of the universe itself, a phenomenon first observed by the astronomer Edwin Hubble in the 1920s. Hubble discovered that distant galaxies are all moving away from us, their light stretched and redshifted due to the expansion of space. This monumental observation led to the realization that the universe is not static, but is constantly growing larger, just as the Big Bang model predicted. Additionally, the relative abundances of those first light elements, hydrogen, helium, and lithium, that we observe in the universe today align perfectly with the predictions of Big Bang nucleosynthesis, serving as a cosmic fingerprint of that first fiery moment. After the formation of those first neutral atoms and the release of that first light, the force of gravity began to take over as the master sculptor of the cosmos. It started to pull the vast clouds of gas and dark matter together, forming the first small clumps of matter. Over hundreds of millions of years, these small clumps grew into larger and larger structures, eventually forming the first stars, the first galaxies, and great clusters of galaxies. These first stars, known as population 3 stars, were massive and short-lived, and through their intense nuclear fusion and spectacular supernova explosions, they forged the heavier elements that would become the building blocks for all future planets, and, eventually, for life itself. The formation of great galaxies, like our own Milky Way, marked the next major milestone in the evolution of the universe. Within these massive, swirling systems of stars, gas, and dust, the cycle of stellar birth and death would continue, constantly enriching the surrounding environment with the heavier elements necessary for the complexity we see today. One of the most intriguing and mysterious discoveries of the past century is the realization that the universe is not only expanding, but is doing so at an accelerating rate. This acceleration is attributed to a mysterious force called dark energy, which is believed to make up about 68% of the universe's total energy content. While scientists have yet to understand the true nature of dark energy, its effects are undeniable, as it continues to drive galaxies farther and farther apart, shaping the ultimate destiny of our cosmos. What is that ultimate fate? It depends on the delicate balance between dark energy and gravity. If dark energy continues to dominate, the universe may expand forever in a scenario known as the Big Freeze, where everything will eventually drift apart, leaving a cold, dark, and empty cosmos. Today, scientists use advanced tools like the James Webb Space Telescope and particle accelerators like the Large Hadron Collider to study the universe's origins and evolution, peering back into the infancy of the cosmos and recreating the conditions of the Big Bang to shed light on the fundamental forces that govern our reality. The story of the Big Bang is not just about the origins of space and time. It is a tale of transformation, of growing complexity, and of the profound interconnectedness of all things. A testament to the power of natural forces and the enduring curiosity of humanity. The universe is a vast, intricate, and mind-bogglingly large system that continues to fascinate and challenge our deepest understanding. Its structure is both magnificently grand and incredibly delicate, with billions of galaxies, great clusters, and enormous voids forming a cosmic tapestry that stretches across unimaginable distances. While it may seem chaotic at first glance, the universe is governed by the fundamental forces of physics, which create beautiful patterns and structures that reflect its dynamic and ever-evolving nature. The part of the universe that we can see, the portion from which light has had enough time to reach us since the beginning of time, is known as the observable universe. It is an immense sphere of space, spanning about 93 billion light-years in diameter. Why is there a limit to what we can see? This limit exists because the speed of light, the fastest thing in the universe, is finite. And the universe itself has a finite age of approximately 13.8 billion years. It is our own cosmic horizon, and beyond it lies a vast unknown expanse of space that we cannot currently detect, but which likely continues in much the same way as the breathtaking region we can see. Within this observable universe, Astronomers estimate there are a staggering 2 trillion galaxies, each one composed of billions, or even trillions, of stars, along with vast clouds of gas, dust, and the mysterious substance known as dark matter. Yet despite this incredible number of objects, the universe is, for the most part, largely empty space, with vast, silent stretches separating these incredible structures. At the very heart of the universe's grand structure are the galaxies themselves, these massive, majestic systems of stars, gas, and dust, all held together in a gravitational embrace. And these great star cities come in a beautiful variety of shapes and sizes. There are the elegant spiral galaxies, which, like our very own Milky Way, feature a flat, rotating disk with graceful spiral arms radiating outward from a bright central bulge. These arms are often ablaze with the light of young, bright stars, while older stars tend to reside in their dense cores. Then, there are the elliptical galaxies, which are more spherical or oval-shaped, like great glowing clouds composed mostly of older stars, with very little gas and dust left for new star formation. And finally, there are the irregular galaxies, which, as their name suggests, lack a defined shape, often because they have been twisted and pulled apart by gravitational interactions with their cosmic neighbors. Our own cosmic home, the Milky Way, is a beautiful spiral galaxy that measures about 100,000 light-years across. It contains somewhere between 200 to 400 billion stars, and at its very center lies a supermassive black hole known as Sagittarius A. But galaxies like ours are not lonely islands. They are often grouped together in great families called galaxy clusters, which can contain hundreds or even thousands of individual galaxies, all bound together by their mutual gravity. And on an even larger scale, these clusters themselves are grouped into what are known as superclusters, the largest known structures in the entire universe. Our own Milky Way is part of the local group, which in turn is part of the immense Laniakea supercluster, a massive cosmic entity containing thousands upon thousands of galaxies. When we zoom out even further, we see that the universe's largest scale structure is often described as a cosmic web. Imagine a vast, three-dimensional network of shimmering filaments, composed of galaxies and clusters, all connected by vast, invisible threads of gas and dark matter. And separating these glowing filaments are enormous, dark voids, vast regions of space that can contain very few galaxies or matter at all. This beautiful web-like structure was sculpted by the patient hand of gravity over billions of years, as matter slowly coalesced into the denser regions while expanding outward from the great voids. But what holds this great cosmic web together? And what is, at the same time, stretching it apart? Here we encounter two of the greatest mysteries in all of science. One is dark matter, a strange, invisible substance that makes up about 27% of the universe's total mass energy content. We cannot see it directly, as it doesn't emit, absorb, or reflect light. But we know it's there because we can observe its powerful gravitational effects on the rotation of galaxies and the structure of clusters. It acts as the invisible scaffolding of the universe, the gravitational glue necessary for these large-scale structures to form and remain stable. Pulling in the opposite direction is another, even more mysterious force, known as dark energy. This force makes up about 68% of the universe's total energy, and is responsible for the accelerating expansion of the universe, a phenomenon discovered in the late 1990s that shows galaxies are moving away from each other at an ever-increasing rate. The interplay between dark energy and gravity will ultimately determine the fate of our universe. This entire grand structure, from stars and planets to the cosmic web itself, is governed by the fundamental force of gravity, which Einstein's general theory of relativity describes as the curvature of space-time itself. It is this force that pulls matter together, forming all the beautiful structures we see today. Stars are the brilliant building blocks of our universe, the great furnaces that provide the light, the heat, and the energy necessary for life as we know it to exist. They are formed from massive, swirling clouds of gas and dust, and they undergo a fascinating and dramatic life cycle. a story governed by the epic interplay of gravity, immense pressure, and the powerful forces of nuclear fusion. Stars come in a dazzling variety of shapes, sizes, and colors, ranging from tiny, dim red dwarfs that sip their fuel for trillions of years, to massive blazing blue supergiants that live fast and die young. Each type of star lives its own unique life, a journey from its birth in a beautiful nebula to its eventual, and often spectacular, death, which may result in a quiet white dwarf, a hyperdense neutron star, or a mysterious black hole. Understanding the life cycle of the stars gives us a precious window into the very processes that shape our cosmos and create the essential elements that make life itself possible. Every star, including our own sun, begins its life in a place of breathtaking beauty, a nebula. Imagine a vast, ethereal cloud of gas and dust, drifting silently in the cold, deep quiet of space. These are the stellar nurseries of our universe. Often a dramatic cosmic event, like the powerful shockwave from a nearby supernova explosion, or the gravitational tug from a passing galaxy, will ripple through one of these serene clouds. This disturbance can cause parts of the nebula to become denser, and in these dense clumps, the patient and relentless work of gravity begins, slowly pulling the swirling gas and dust together into ever larger clumps. Over immense periods of time, these clumps continue to grow, collapsing under their own immense gravity and forming what is known as a protostar, the earliest, embryonic stage of a star's life. As the protostar continues to contract, its core temperature and pressure begin to build to almost unimaginable levels. And then, when the core temperature finally reaches about 10 million Kelvin, a miracle of physics occurs. Nuclear fusion begins. In this incredible moment, the star ignites. In its heart, a powerful nuclear furnace begins the process of fusing hydrogen atoms together to form helium, releasing an enormous amount of energy in the process. This new outward-pushing pressure from the fusion furnace perfectly balances the inward-crushing pull of gravity, halting the protostar's collapse and bringing it into a state of equilibrium. At this point, the star is truly born, and it enters the longest and most stable period of its entire life, a phase known as the main sequence. During its time on the main sequence, a star achieves this beautiful balance, allowing it to maintain a stable size and to shine steadily for millions, or even billions, of years. But not all stars live the same life. Their destiny is determined by their mass. Low-mass stars, like the dim red dwarfs, are incredibly frugal with their fuel. They burn their hydrogen so slowly that they can remain on the main sequence for tens of billions, or even trillions, of years. In stark contrast, the massive, brilliant blue giants are incredibly extravagant, burning through their fuel with incredible speed, and may leave the stability of the main sequence after just a few million years. Our own sun is a typical main sequence star, classified as a G-type yellow dwarf. It has been shining steadily in this phase for about 4.6 billion years, and it is expected to remain stable for another 5 billion years to come. During this long and placid Middle Age, the nuclear fusion in our sun's core continues to produce the light and heat that have sustained the evolution of life on our own planet. But what happens when a star begins to run out of the hydrogen fuel in its core? This marks the beginning of the end of its time on the main sequence. As the hydrogen fusion slows, the delicate balance between gravity and pressure is broken. Gravity once again takes over, causing the core to contract and heat up to even more extreme temperatures. This new, intense heat becomes hot enough to ignite the fusion of the helium that was created earlier, forging heavier elements like carbon and oxygen. Meanwhile, the outer layers of the star, pushed outward by this new, more powerful furnace in the core, begin to expand dramatically. The star swells to an immense size, becoming what is known as a red giant, or, for the most massive stars, a red or blue supergiant. For stars like our own sun, the red giant phase will be a brief but truly spectacular period of expansion. Billions of years from now, our sun will eventually swell to many times its current size. potentially engulfing the inner planets of our solar system, including the Earth. During this phase, the star will lose much of its outer material through powerful stellar winds, creating a beautiful and luminous shroud of glowing gas known as a planetary nebula. The massive stars, the supergiants, will undergo a much more dramatic and violent transformation. In their intensely hot cores, they can forge even heavier elements like silicon and iron. But once the core begins to create iron, the process of fusion can no longer produce any more energy. This signals the star's impending, spectacular death, a story we will explore in our next chapter. The life of a star is a magnificent story of creation, a cosmic forge where the very elements necessary for life are made. But just as they are born, so too must they die. And it is in their spectacular deaths that they give their final, most profound gifts to the universe. Black holes and neutron stars represent the most extreme and fascinating outcomes of stellar evolution, showcasing the universe at its most mysterious and its most powerful. These incredible celestial objects are born from the death of the most massive stars, and they push the very limits of physics, of gravity, and of our understanding of the cosmos itself. While black holes are enigmatic regions of space where gravity is so overwhelmingly strong that nothing, not even light itself, can escape. Neutron stars are incredibly dense remnants of stars that manage to pack more mass than our entire sun into a sphere that is only a few kilometers across. Both of these strange objects originate from the final, violent collapse of massive stars at the very end of their life cycles. When a massive star finally exhausts the nuclear fuel in its core, it can no longer generate the outward pressure needed to resist the relentless inward pull of its own immense gravity. For stars with masses greater than about 8 times the mass of our sun, this final collapse results in one of two spectacular outcomes, depending on the remaining mass of the core after a magnificent supernova explosion. First, let's consider the fate of a star whose remaining core has a mass between about 1.4 and 3 times that of our sun. In this case, the gravitational collapse is halted by a powerful quantum mechanical effect known as neutron degeneracy pressure, a fundamental force that arises from the repulsion between tightly packed neutrons. The result is an unbelievably dense object called a neutron star, which may have a diameter of only about 10 to 20 kilometers, but contains a mass greater than our sun. To put their incredible density into perspective, a single sugar cube-sized amount of neutron star material would weigh billions of tons here on Earth. These stellar remnants are composed almost entirely of neutrons, with their interior resembling a single, giant atomic nucleus. Some of these neutron stars have magnetic fields that are trillions of times stronger than Earth's, and when they rotate with incredible speed, they can emit powerful beams of electromagnetic radiation from their magnetic poles, becoming what we call pulsars. These beams sweep across space like a great cosmic lighthouse, and when observed from Earth, they appear as incredibly regular, periodic flashes of light. Pulsars are so precise, with some spinning hundreds of times per second, that they are considered nature's most accurate clocks. But what happens if the star's collapsing core is even more massive? If the core's mass exceeds about 3 times the mass of our sun, then gravity, the ultimate force of the cosmos, overwhelms all other opposing forces. The core continues to collapse indefinitely, crushing down into a singularity, a point of infinite density. The region of space around this singularity, from which nothing can escape, is called the event horizon, and this marks the boundary of a black hole. We cannot, by definition, see a black hole directly, as not even light can escape its gravitational pull. Instead, their presence is inferred by the powerful way they affect the nearby objects around them, such as stars, gas, and dust. There are several types of black holes. Stellar black holes form from the collapse of individual massive stars and typically have masses between 3 and 20 times that of our sun. And at the centers of most galaxies, including our own Milky Way, we find supermassive black holes, true titans, with masses ranging from millions to billions of times the mass of our Sun. The defining feature of a black hole is its event horizon, the point of no return. Beyond this boundary, space-time is so incredibly curved that all paths lead inward to the singularity at the centre. Black holes also exhibit other fascinating phenomena, such as gravitational time dilation, where time itself slows down near a black hole relative to an observer farther away. This effect, predicted by Einstein's general theory of relativity, means that for someone near a black hole, mere seconds could pass, while years go by for a distant observer. And in a theoretical process proposed by the physicist Stephen Hawking, it suggested that black holes can slowly emit particles over immense periods of time, which could eventually cause them to lose mass and evaporate. Both black holes and neutron stars play significant roles in the cosmos. They are the endpoints of massive stars, marking the final dramatic stages of stellar evolution and enriching the universe with the heavy elements that were forged in their supernova explosions. Their immense gravitational pull influences their surroundings, shaping the motion of stars and gas in their vicinity. And they serve as natural laboratories for studying the absolute extremes of physics. When two neutron stars or two black holes collide, they produce gravitational waves, great ripples in the fabric of space-time itself, which were first detected in 2015. These incredible mergers also release massive amounts of energy and forge the heaviest elements in the universe, like gold and platinum. These fascinating objects, born from the death of stars, challenge our understanding of physics and offer us tantalizing glimpses into the fundamental nature of reality itself. The solar system is our cosmic neighborhood, a vast and wonderfully fascinating system that is dominated by the immense gravitational presence of the Sun, and it is home to a beautiful variety of planets, moons, asteroids, comets, and countless other celestial objects. Our home system was formed around 4.6 billion years ago, and it offers us a precious window into the very processes that govern the universe, from the birth of stars like our own Sun to the intricate formation of planetary systems. While we have explored only a tiny fraction of its many wonders, the solar system remains a primary focus of scientific discovery, constantly sparking our curiosity and expanding our understanding of the cosmos. The story of our solar system begins, as all stellar stories do, with a giant cold molecular cloud composed of gas and dust, drifting silently in the vastness of space. A nearby cosmic event, perhaps the powerful shockwave from a dying star's supernova explosion, likely triggered the gravitational collapse of this great cloud, causing it to begin to spin and flatten into a vast, rotating protoplanetary disk. At the very center of this swirling disk, where matter was most concentrated, our Sun was formed, growing hotter and denser until it finally ignited with the fire of nuclear fusion, becoming the system's primary source of all its energy and light. And what of the remaining material in that great disk? Through a process known as accretion, this material began to coalesce, a cosmic dance of dust and gas slowly coming together over millions of years to form the planets, the moons, and all the other objects that make up our system today. The layout of our solar system was determined by the conditions in that early, chaotic disk. Close to the intense heat of the young Sun, only rocky materials could withstand the high temperatures, leading to the formation of the 4 terrestrial planets: Mercury, Venus, Earth, and Mars. Farther out, where the temperatures were much cooler, gas and ice giants like Jupiter, Saturn, Uranus, and Neptune could form. And beyond the orbit of the farthest planet, Neptune, lies the Kuiper Belt, a vast, cold region of icy bodies, and even farther still, the theoretical Oort cloud, the distant source of our long-period comets. Our Sun, a yellow dwarf star, is the undisputed heart of our solar system, comprising over 99.8% of the system's total mass, and exerting gravitational control over every other object within it. It generates its incredible energy through the constant fusion of hydrogen into helium in its core, releasing the light and heat that have sustained life on our own planet for billions of years. Let's take a brief tour of this neighborhood. The inner solar system is home to the small, rocky, terrestrial planets. There is Mercury, the closest planet to the Sun, a barren and heavily cratered world with the most extreme temperature fluctuations in the solar system. Next is Venus, often called Earth's twin due to its similar size, but it is a hellish world with a thick, crushing atmosphere of carbon dioxide and clouds of sulfuric acid, making it the hottest planet in our solar system. Then, there is our home, Earth, the only planet we know of that supports life, with its diverse climates, a protective atmosphere, and abundant liquid water. And finally, there is Mars, the red planet, known for its iron-rich soil, its polar ice caps, the largest volcano in the solar system, Olympus Mons, and a massive canyon system known as Valles Marineris. The outer solar system is the realm of the giants. Jupiter, the largest planet, is a gas giant with a strong magnetic field, and its famous Great Red Spot, a massive storm that has raged for centuries. Saturn is renowned for its iconic and beautiful ring system, which is made of countless particles of ice and rock. And beyond lie the ice giants. Uranus, which has a bluish-green hue and mysteriously rotates on its side. And Neptune, the farthest planet, a world of intense winds and powerful storms. Our solar system is also teeming with a dazzling variety of moons, each a unique world in its own right. There is Jupiter's icy moon, Europa, which has a vast subsurface ocean, making it a prime candidate in the search for extraterrestrial life. There is Saturn's moon Titan, known for its thick atmosphere and lakes of liquid methane, a world that might resemble the early Earth. And there is Jupiter's moon Io, the most volcanically active body in the entire solar system. Humanity, with its endless curiosity, has sent numerous robotic probes to explore these wonders. The Voyager spacecraft, launched in 1977, have now travelled beyond our solar system into interstellar space. Rovers like Perseverance and Curiosity have uncovered evidence of Mars's watery past, while missions like Cassini and New Horizons have given us breathtaking views of Saturn and Pluto. The solar system is not just our home, it is a cosmic laboratory, a place of immense beauty and diversity. And as we continue to explore it, we uncover new mysteries and deepen our understanding of the dynamic system we are so lucky to be a part of. The Moon, Earth's only natural satellite, has been a subject of fascination for humanity since the dawn of our species, serving as a beacon of wonder, a source of inspiration for poets and artists, and a driver of profound scientific discovery. Its powerful influence on our planet extends far beyond its ethereal and gentle beauty in the night sky. From stabilizing Earth's rotation to driving the rhythm of our ocean tides, the Moon plays an absolutely critical role in maintaining the very conditions that make our planet habitable. Over the past century, the Moon has also become a focal point for our ambitions in space exploration, representing humanity's first tentative steps beyond our home world, and our deep aspirations for even grander cosmic ventures. How was our constant companion born? The most widely accepted scientific theory, known as the giant impact hypothesis, suggests a birth of truly epic and violent proportions. The story begins about 4.5 billion years ago, shortly after the birth of our solar system, when a Mars-sized body, an ancient protoplanet often referred to as Theia, collided with the young Earth in a catastrophic impact. Can you imagine the power of such an event? It would have ejected massive amounts of molten debris from the Earth into orbit around our planet. Over time, the patient and relentless force of gravity worked its magic, and this great cloud of orbiting material coalesced to form the Moon we see today. This dramatic theory beautifully explains many of the Moon's unique characteristics, such as its lower density compared to Earth and the similar composition of certain isotopes that are found in its rocks. The Moon's initial surface was likely covered in a vast, global ocean of molten rock, which gradually cooled and solidified over millions of years to form the rugged and beautiful landscape we see today. The Moon is a relatively small celestial body, with a diameter only about 1/4 the size of Earth's. Despite its size, its close proximity to our planet gives it a significant gravitational influence. Its surface is a world of stark and silent beauty, a tale of two distinct terrains. There are the highlands, the lighter-coloured regions that are older and heavily cratered, which make up most of the moon's surface. And then there are the Maria, the darker, smoother plains that are actually vast basaltic regions formed by ancient volcanic activity. Early astronomers mistakenly thought these dark patches were actual bodies of water, which is why they gave them the Latin name for seas. And of course, the moon's entire surface is pockmarked with craters, the ancient scars of asteroid and comet impacts that have accumulated over billions of years. The moon's influence on Earth is truly profound. Its gravitational pull creates the rhythmic ocean tides, which play a crucial role in shaping our coastal ecosystems and helping to redistribute heat across the planet. And perhaps, most importantly, the moon's gravity helps to stabilize Earth's axial tilt, preventing it from fluctuating wildly over time. Without our moon, Earth's axis could shift dramatically, which would lead to extreme and catastrophic changes in our climate that could make life, as we know it, impossible. The moon has even, over billions of years, gradually slowed Earth's rotation, lengthening our days from what may have once been as short as just 6 hours. For centuries, the moon was a target of human curiosity, a dream just out of reach. But in the 20th century, that dream became a reality. The Apollo program, conducted by NASA between 1961 and 1972, stands as one of the greatest achievements in all of human history. In 1969, with the Apollo 11 mission, the astronauts Neil Armstrong and Buzz Aldrin became the first humans to walk on the lunar surface, delivering those famous and immortal words, "That's one small step for a man, one giant leap for mankind." The subsequent Apollo missions explored other lunar regions, conducted important experiments, and collected invaluable rock samples that helped scientists understand the moon's history and its deep connection to our own planet. In recent years, our interest in the moon has surged once again. Programs like NASA's Artemis aim to return humans to the lunar surface, but this time with the ambitious goal of establishing a sustainable presence that could serve as a vital stepping stone for future missions to Mars and beyond. The moon is an invaluable time capsule for studying the early solar system. Its lack of an atmosphere means its surface has remained largely unchanged for billions of years, holding precious clues about the period of heavy bombardment that shaped all the planets. And recent discoveries of water ice in permanently shadowed craters at the moon's poles have opened up incredible possibilities for producing oxygen, drinking water, and even rocket fuel on site, which could be essential for long-term space exploration. The moon is so much more than just a beautiful celestial body orbiting our Earth. It is a vital part of our planet's story and our future, a constant reminder of our place in the vast cosmos and our enduring ambition to reach for the stars. The universe is filled with extraordinary and enigmatic phenomena that continue to captivate scientists and astronomers. Great cosmic mysteries that challenge our understanding of physics and the very nature of reality. From the dazzling, gentle auroras that dance in our own skies, to the mind-bending concepts of dark matter and parallel universes, the cosmos is a treasure trove of wonders that remind us of how much we still have to learn. These phenomena not only highlight the dynamic and often unpredictable nature of the universe, but also serve as powerful reminders of the endless frontiers still waiting to be explored. Let's begin here, on our own planet, with one of the most beautiful and accessible of all cosmic phenomena, the aurora. Often called the Northern Lights, or Aurora Borealis in the Northern Hemisphere, and the Southern Lights, or Aurora Australis in the Southern Hemisphere. These vibrant, dancing displays of light in our polar skies are caused by a beautiful interaction between our planet and our star. When the solar wind, a constant stream of charged particles from the sun, collides with Earth's protective magnetic field, some of these particles are funneled down towards the polar regions. There, they interact with the gases in our upper atmosphere, causing them to emit light. The specific beautiful colours of an aurora depend on which gas is being excited and at what altitude. Oxygen gives us the common, ethereal green and the rarer, higher altitude red auroras, while nitrogen can create beautiful blues. These celestial light shows are not unique to Earth. They have also been observed on other planets with strong magnetic fields, such as Jupiter and Saturn. From the gentle beauty of the aurora, let's turn to the most energetic and violent explosions in the entire universe: gamma-ray bursts, or GRBs. Can you imagine an explosion so powerful that it releases more energy in just a few seconds than our Sun will emit in its entire 10 billion year lifetime? These incredible bursts of energy are thought to occur during two of the most cataclysmic events the universe has to offer: the collapse of a truly massive star as it forms a black hole or a neutron star, or the spectacular collision of two hyperdense neutron stars. These events are so powerful they also create gravitational waves, great ripples in the very fabric of space-time itself. These explosions are also responsible for forging and scattering many of the heaviest elements in the universe, like gold and platinum. Now, let's look for the brightest objects in the universe. These are the quasars, which are among the most luminous objects known, powered by the supermassive black holes that lurk at the centers of distant young galaxies. As immense amounts of gas and dust spiral into one of these giant black holes, they form a brilliant, superheated accretion disk, which emits an almost unimaginable amount of intense radiation. A quasar can be so bright that it can outshine the entire galaxy it resides in, making it visible to us from billions and billions of light years away. They provide us with a precious window into the early universe, allowing us to study a time when galaxies were still forming. One of the newest cosmic mysteries that has astronomers completely captivated are fast radio bursts, or FRBs. These are intense, but incredibly brief, millisecond-long bursts of radio waves that seem to originate from distant galaxies. Their exact cause remains completely unknown, though some theories suggest they may be related to highly magnetized neutron stars called magnetars. Their random and fleeting nature makes them incredibly difficult to study, but they are a thrilling cosmic puzzle, and perhaps the greatest mysteries of all are the ones we cannot see. While the visible matter of stars and galaxies is what we are familiar with, it makes up only about 5% of the universe's total mass energy content. The rest is composed of two mysterious components: dark matter, which makes up about 27% of the universe, and dark energy, which makes up about 68%. Dark matter is the invisible scaffolding that holds our galaxies together, detectable only through its gravitational effects. Dark energy, even more mysterious, is the force that is causing the expansion of our universe to accelerate, driving everything farther apart. Their true nature remains one of the greatest unsolved puzzles in all of science. The concept of the multiverse, while speculative, suggests that our universe may be just one of countless others, an idea that arises from deep theories in modern physics. And rippling through all of this are gravitational waves, first predicted by Einstein, which are disturbances in space-time caused by massive cosmic events, allowing us to study the universe in a completely new way. The universe is full of phenomena that stretch the boundaries of our knowledge and our imagination. These cosmic mysteries remind us of how much there is still to explore. As our technology advances, we move ever closer to unraveling these great enigmas, shedding more light on the vast and wondrous universe we call home. And with that thought, our journey through the secrets of space comes to a close. Let the wonders of the cosmos, the nebulae, the galaxies, and the distant worlds fill your mind as you drift off to sleep. Good night, and have cosmic dreams. Space exploration is undeniably one of humanity's greatest and most inspiring endeavors. It represents our innate and unyielding drive to uncover the unknown, to venture into the void, and to push the boundaries of what we believe we can achieve. Over the past century, incredible advancements in space technology have completely transformed our understanding of the universe, allowing us to explore planets, moons, asteroids, and the vast emptiness beyond. From the very first human-made object to leave Earth's atmosphere to the sophisticated, intelligent rovers that are now roaming the surface of Mars, the story of space exploration has not only expanded our scientific knowledge, but has also inspired generations to dream bigger and to look up at the night sky with a profound sense of wonder. It is a story of breathtaking innovation, of incredible perseverance, and of the collective effort of humanity to reach for the stars. Our journey into space began in earnest during the tense years of the Cold War, fueled by an intense political and ideological rivalry between the United States and the Soviet Union. The starting pistol for this great space race was fired on October 4th, 1957, when the Soviet Union successfully launched Sputnik 1. This small basketball-sized satellite was the very first human-made object to ever orbit the Earth, and its simple beeping signal sent shockwaves of both awe and anxiety around the world. The United States quickly responded with its own ambitious space program, leading to a period of breathtaking, groundbreaking achievements in an incredibly short amount of time. In 1961, the Soviet cosmonaut Yuri Gagarin became the first human to ever travel into space, orbiting our planet aboard his Vostok 1 capsule. The United States soon followed with Alan Shepard, the first American in space, and later, John Glenn, who became the first American to orbit the Earth. This incredible race to space, a competition for technological and ideological supremacy, reached its absolute pinnacle in the summer of 1969. This was the year that NASA's Apollo 11 mission achieved a dream as old as humanity itself. It landed humans on the moon. The astronauts Neil Armstrong and Buzz Aldrin became the first people to ever walk on the lunar surface, while their crewmate, Michael Collins, piloted the command module in lunar orbit. These early, heroic milestones powerfully demonstrated humanity's incredible ability to explore beyond our home planet and laid the essential foundation for all the ambitious missions that would follow in the decades to come. In recent decades, robotic missions have taken center stage in our exploration of the cosmos. These incredible probes, landers, and rovers allow us to study distant and often dangerous worlds without the immense risks and costs of sending human astronauts. Let's meet some of these remarkable robotic explorers. There are the Voyager 1 and 2 spacecraft, which were launched way back in 1977. They explored the outer planets of our solar system before continuing their incredible, lonely journey into interstellar space. Voyager 1 is now more than 14 billion miles from Earth, the farthest human-made object in the universe, still sending back precious data from the void. And what about the Red Planet? NASA's Mars rover missions, including Spirit, Opportunity, Curiosity, and Perseverance, have provided us with invaluable insights into the geology and climate of Mars. These rovers have discovered clear and undeniable evidence of ancient rivers and lakes, suggesting that Mars may have once been a much warmer, wetter, and possibly habitable world. The Cassini-Huygens mission explored the beautiful ringed planet, Saturn, and its fascinating moons, including Titan, with its lakes of liquid methane, and Enceladus, which ejects great plumes of water from its subsurface ocean. In 2015, the New Horizons mission made history by flying past the dwarf planet Pluto, revealing a surprisingly complex and active world at the very edge of our solar system. And today, our greatest eye on the cosmos is the magnificent James Webb Space Telescope. Launched in 2021, it is the most advanced and powerful space observatory ever built. It allows scientists to peer back in time to study the formation of the very first galaxies and stars, and it is a crucial tool in our ongoing search for the signs of life on distant exoplanets. The story of space exploration, from that first simple satellite to the sophisticated rovers now roaming Mars, has not only expanded our knowledge of the universe, but it has also inspired generations to dream bigger. It is a testament to human ingenuity, our unyielding curiosity, and our determination to overcome any challenge in our quest to understand our place in the cosmos. Space exploration is one of humanity's greatest and most ambitious endeavors, representing our innate drive to uncover the unknown and to push the boundaries of what we can achieve. In recent years, we have entered a vibrant new era, one driven by both government agencies and ambitious private enterprises, all working to expand our presence beyond Earth and to explore the farthest reaches of the cosmos, This quest to reach for the stars not only seeks to answer fundamental questions about the universe, but also aims to ensure the long-term survival of humanity itself. For decades, one of our greatest achievements in space has been the International Space Station, or ISS. Launched in 1998, the ISS is a remarkable collaborative effort involving space agencies from the United States, Russia, Europe, Japan, and Canada. Orbiting our planet at an altitude of about 260 miles, it serves as a unique laboratory in the sky. Astronauts aboard the ISS conduct crucial experiments in microgravity, studying everything from human physiology to material science, and it has served as a vital testbed for the technologies that we will need for future long-duration missions to the Moon, to Mars, and beyond. In recent years, the entire landscape of space exploration has been completely revolutionized by the rise of private companies, which are dramatically reducing costs and increasing our access to space. Companies like SpaceX, founded by Elon Musk, Blue Origin, founded by Jeff Bezos, and Rocket Lab, are leading the way in this new era of commercial spaceflight. SpaceX, for example, developed the Falcon 9, a reusable rocket that has significantly lowered the cost of launching satellites and supplies into space. This reusable rocket technology is a true game changer, making space exploration more sustainable and affordable than ever before. These companies are not only supporting government missions, but are also pioneering new frontiers like space tourism, offering civilians the opportunity to experience weightlessness and to view our beautiful Earth from the blackness of space. And this new era of exploration has incredibly ambitious goals. One of the most immediate is a return to the Moon, this time to stay, through NASA's Artemis program. Unlike the short visits of the Apollo missions in the 1960s and 70s, Artemis aims to establish a sustainable human presence on the Moon by the end of this decade. The key objectives include landing the first woman and the first person of color on the lunar surface, and building the Lunar Gateway, a space station that will orbit the Moon and serve as a staging point for future lunar missions. The Moon is seen as a crucial stepping stone, a place where we can learn to live and work on another world before we take our next great leap into the solar system. And what is that next great leap? Mars. The red planet has become the focal point of our ambitions for human exploration beyond the Moon, with its potential for past habitability and its resources. NASA has a stated goal of sending humans to Mars in the 2030s, using the technologies that will be developed and proven through the Artemis program. And private companies like SpaceX are developing immense new rockets, like the Starship, with the explicit aim of creating a fleet of reusable spacecraft capable of transporting humans and cargo to Mars, with the ultimate and audacious goal of making humanity a multi-planetary species. Of course, the challenges of sending humans to Mars are immense, from developing reliable life support systems and protecting astronauts from harmful radiation on the long journey, to creating the powerful propulsion technologies needed for the trip. But many see the eventual colonization of Mars as a critical step for ensuring the long-term survival of humanity in the event of a global catastrophe here on Earth. The search for extraterrestrial life also remains one of the most compelling motivations for our future exploration. Upcoming missions, like the Europa Clipper, will study the icy moons of Jupiter, like Europa and Ganymede, which are thought to have vast subsurface oceans with the potential to harbour life. And while travel to other stars remains a distant dream, scientists are already exploring theoretical propulsion systems like nuclear fusion rockets and antimatter drives that could one day allow humanity to reach other star systems. Projects like Breakthrough Starshot, which aims to send tiny, light-powered probes to Alpha Centauri, our nearest star system, represent humanity's very first tentative steps toward exploring beyond our own solar system. The future of space exploration holds an almost limitless potential. It is a testament to our species' innate curiosity and our unyielding desire to explore. The journey to the stars is only just beginning, and the possibilities are as vast and wondrous as the universe itself. Of course. Let's embark on the final chapter of our journey. We have explored the birth of the cosmos, the lives of stars, and humanity's own quest to reach for them. For our final chapter, let us now drift through the universe and marvel at some of the most extraordinary and enigmatic phenomena it has to offer, cosmic mysteries that continue to challenge our understanding of reality itself. The search for planets beyond our solar system, these distant worlds known as exoplanets, has truly revolutionized our understanding of the universe. It has raised profound and deeply humbling questions about the possibility of life existing elsewhere in the cosmos. Since the groundbreaking discovery of the first exoplanet orbiting a sun-like star back in 1995, scientists have successfully identified over 5,000 of these distant worlds, with more being discovered every single year. These planets come in a truly dazzling variety of sizes, compositions, and orbital configurations, challenging all of our traditional ideas about how planetary systems can form and what forms they can take. The great quest to study exoplanets is not just about cataloguing distant worlds. It's a profound search for answers to some of humanity's oldest and most fundamental questions. Are we alone in the universe? And how common is life among the countless stars? Exoplanets, these planets that orbit stars far outside our own solar system, range from strange, hot Jupiters, which are massive gas giants orbiting incredibly close to their parent stars, to super-Earths, rocky planets that are larger than our own world but smaller than a planet like Neptune. These worlds are often dramatically different from the planets in our own solar system, demonstrating the incredible diversity of planetary systems across our galaxy. But of all these thousands of newfound worlds, the ones that truly capture our imagination are those that might be like our own. One of the most critical aspects of this search is determining whether a planet falls within what is known as the habitable zone, an area often affectionately called the Goldilocks zone. This is the region around a star where the conditions are not too hot, not too cold, but just right for liquid water to exist on a planet's surface, a key and essential ingredient for life as we know it. But how do you find a tiny, dim planet orbiting a brilliant star that is hundreds or even thousands of light years away? It is an incredible technical challenge because these planets are incredibly distant and often lost in the overwhelming glare of their parent stars. However, astronomers have developed some truly ingenious and clever methods to find and study these distant worlds. The most successful technique is known as the transit method. Imagine watching a distant star and seeing its light dip ever so slightly on a regular, periodic basis. This tiny dip in brightness is caused by a planet passing in front of the star from our point of view, an event known as a transit. NASA's famous Kepler Space Telescope used this very method to discover thousands of exoplanets by patiently monitoring the light from distant stars. Another clever technique is the radial velocity method. This method measures the tiny wobble of a star, which is caused by the gravitational pull of its orbiting planet. This wobble causes detectable shifts in the star's spectral lines, which can be measured by sensitive instruments here on Earth. In some very rare cases, astronomers can even directly photograph exoplanets by using powerful telescopes equipped with special instruments that block out the star's brilliant light. Over the years, several of these distant worlds have truly captured the imagination of scientists and the public alike. There is Kepler 22b, one of the first potentially habitable exoplanets ever discovered, which is located in its star's habitable zone. There is Proxima Centauri b, which orbits the very closest star to our solar system, just over 4 light-years away, making it a tantalizing target for future interstellar missions. And perhaps most famously, there is the TRAPPIST-1 system, located 40 light-years away, which contains an incredible 7 Earth-sized planets, 3 of which orbit within the habitable zone, making it one of the most intriguing systems in our search for extraterrestrial life. One of the most exciting goals of all this research is the search for what are known as biosignatures, chemical or physical markers in a planet's atmosphere that could indicate the presence of life. Powerful new instruments, like the James Webb Space Telescope, are designed to analyze the atmospheres of these distant worlds, searching for telltale signs like high levels of oxygen and ozone, or the presence of methane and water vapor. The discovery of life beyond Earth remains an extraordinary challenge. The conditions necessary for life, as we know it, are likely rare and are incredibly difficult to confirm from such vast distances. Furthermore, life on other planets might be completely unlike life on Earth, potentially existing in forms we cannot yet imagine. But the study of exoplanets goes beyond just the search for life. It provides us with deep insights into how planets form and evolve, the incredible diversity of planetary systems, and the general conditions necessary for habitability. By studying these distant worlds, scientists can better understand the processes that shaped our very own solar system and the factors that allowed life to emerge here on Earth. The discovery of exoplanets has opened an entirely new frontier in astronomy, bringing us closer than ever to answering those age-old questions about life beyond our world. This search reminds us of the vastness and the diversity of the universe and the endless, wondrous possibilities it holds.